Hey everybody, it's Mrs. Harbin. We're doing video notes 11.1, so there's 5 things you should be able to do. Read these. By the end of the unit, that's 5 of the things that we're going to be able to do. Okay? Those are our objectives. Alright, Chapter 19, Sections 19.1 and 19.3 are in there. I better do my shout out now or else I'll forget. But everybody, GOL, thanks Maddie and Brittany for the suggestion. Hee. Alright. And also, I meant to play this song last time because we disturb an equilibrium. Get it? Yeah. Okay, I'll stop now. Anyway, so our unit this time is about acids and bases. So we're going to talk about properties. So we got to give acids and bases their props. Props, yeah, give them the props. So there's acids, there's bases, and there's neutral things. Acids taste sour, and bases a lot of times taste bitter. Okay, it's not always true, but those are 2 common characteristics of acids and bases. And neutral things, of course, taste like chicken. That was a joke, people. It's just, you know, what does it taste like? Tastes like chicken. That's what everybody says. But anyway, neutral things can taste like whatever they taste like. Acids feel, well, sometimes they, like, you might feel a sting, or they might burn a little bit if you get it on your skin. Bases, on the other hand, feel slippery. Yes, you can still get chemical burns from bases or chemical damage on your skin, but it's slippery at first, and then, you know, it just eats away your layers of skin. Neutral things, on the other hand, always feel guilty. Okay, another joke, folks. All right, litmus. Litmus is called an indicator, and litmus changes colors when it's exposed to acids or bases. If litmus is exposed to acid, it'll turn red. Turns red. Okay, so blue to red, litmus. Litmus turns red. Blue to red, acid, and base turns blue. Turns litmus blue. Okay, so litmus is an indicator, and it indicates an acid by turning red. It indicates a base by turning blue. Neutral things will not change litmus paper's color. Phenolphthalein is another indicator, and in an acid it turns clear. Okay, and in a base it turns violet. And actually, you saw phenolphthalein in the equilibrium lab with the pretty purple color. Okay, in neutral things, phenolphthalein is also clear. All right, conductivity. Conductivity is the ability to conduct electricity. Acids, yes, they conduct, okay? Why? Because acids, when they dissolve in water, make ions. Bases also conduct electricity because bases, when they dissolve in water, make ions. Neutral things conduct electricity if they're ions in the neutral substance, but they do not conduct electricity if there are no ions. Okay, so this is not something that tells them apart, but it is a characteristic of acids and bases. pH is less than 7 for acids, and bases, the pH is over 7. So what does 7 mean? 7 means a neutral substance. If you add a metal to an acid, it reacts. Okay. If you add metal to a base, it's no reaction. No reaction. If you add a metal to neutral things, there's usually no reaction. Okay. Add carbonate or like limestone, marble type stuff to acids, it reacts. Okay. But if you add it to bases, it's no reaction. And if you add it to neutral things, it's not. So some ways to tell them apart are their properties. Some things they have similar properties, but we're going to be discussing the chemistry of acids and bases. So let's talk about vinegar. Vinegar is an acid. Okay. Ammonia, you may have heard of ammonia. Ammonia is a base. A lot of cleaning supplies. Some cleaning supplies are acids or bases. Both of them can be used as cleaning supplies. Right? Like soap is a base, but the stuff for a toilet bowl cleaner is an acid. OJ, orange juice, is an acid. It's acidic, and gastric juices are acidic. So places you find acids in your house, places you find bases in your house, places you find acids, stuff you drink. Okay, so how do chemists view acids and bases? There are definitions of it. Remember when we first talked about acids, they start with hydrogen. So it's, hello, I start with hydrogen, I'm an acid. Okay, so 2 different definitions that you'll have to understand. The Arrhenius definition is pretty simple. It was the first definition of acids and bases that was developed scientifically. Acids have H+, and bases have OH-. So things that have hydrogen in them are acids, things that have hydroxide are bases. The Bronsted-Lowry definition is that acids are H+ givers and bases are H+ takers. Another way of saying that same thing is that acids donate protons, so an H+ is a proton. And bases accept H+, so bases take protons from other things. All right, so H+ is a proton, acids give protons away. Bases take protons, which means they take H pluses. So these two definitions, let's use them here. Okay, so on this, which one's an acid? Hello, I'm an acid. I start with hydrogen. And then here's the hydroxide, so this is the base. Okay, so what about this one? Oh, I switched it up. This is the base. It's got hydroxide. And this is the acid because, hello, I start with hydrogen. Okay, so one way to figure it out is to use the Arrhenius definition. If we're using the Bronsted-Lowry definition, then every acid, you know it's an acid because of what it turns into, and what it turns into is a base. And every base turns into what's called a conjugate acid. So let's see, HCl, these two things are a pair. The HCl turns into a Cl minus. Why? Because the HCl gives away its H plus. So this is an acid because it gives away H plus to turn into Cl minus. Okay, that means this is the conjugate base of that acid, conjugate base. All right, so let's check out this pair of things. Oops, sorry about that. Going from left to right, this H2O takes an H plus. Where does it get it? It gets it from the acid, but H2O turns into H3O plus. So it's got an extra H and a plus. So this is a base because it's a proton acceptor or H plus taker. And so this is the conjugate acid of that base. Okay, so it's really a conjugate and acid-base pair. All right, so what does the NH3 do? NH3 turns into NH4 plus. In order to turn into NH4 plus, it has to take an H and a plus. So this must be a base because it's a proton taker. And then this must be the conjugate acid. Conjugate acid. All right. Is there another pair here? Oh, looks familiar. All right, so here's HCl. It turns into Cl minus. What happens? It gives away an H and a plus. So this must be an acid because it's a proton donor, proton giver, and it turns into a conjugate base. Conjugate base. All right, we'll keep practicing. Next, what if you see H plus and then you see H3O plus? You might be saying to yourself, what's different? What's the same? Well, they are the same. They represent the same thing. Okay. If H plus is produced when you put an acid into water, where does the H plus go? It always attaches to the water molecules. So H plus and H3O plus are interchangeable. They mean the same thing. Okay, they're always together. Kind of like, you know, that annoying couple in the hallway. How can they always be together? Well, they're like H plus and H3O plus. Water and acid, look, this attaches to that. All right, so let's get another thing to talk about, and that's acid strength and base strength. You need to memorize the strong acids and bases, but you also need to know what it means for them to be strong. So strong acids and bases, what makes them strong is their ability to ionize 100%. They completely turn into ions when you put them into water. Strong acids, there are 6 of them, 1, 2, 3, 4, 5, 6. Memorize them. Okay, that means when I take HCl and put it into water, it's not HCl anymore. It's H plus and Cl minus, all broken apart, floating around in that container totally. Okay, strong bases, same thing. They ionize completely. How do you know the strong bases? Well, you look at the periodic table. Ooh, look at the periodic table. Here's group 1. Here's group 2. So you got lithium and sodium and potassium, and over here you have beryllium and magnesium and calcium. Any element in these groups that mixes with hydroxide to make a compound is a strong base. All right, so hydroxides of these are strong bases. So let's look at HNO2. What is it? It's an acid. Hello, I start with hydrogen. NO2. It's not on this list, so it must be a weak acid. Sorry, weak acid. Hello, I'm an acid. But it's a weak one because it's not on the list. CaOH. Well, OH means base, and Ca is in group 2, so this is a strong base. All right, HCl. Hello, I'm an acid. Okay, so HCl is on the strong list, so this is a strong acid. And then we're looking at this going, wait, there's no H plus, there's no OH minus. What the heck is it? This is ammonia. Please memorize that ammonia is a base. It's not a base in these groups, so this is a weak base. All right. Next, concentration does not equal strength. These are two different things. It's a huge concept in chemistry that we have to be able to distinguish. Strength, we just learned, is all about the ions, the ions, the ions. Lots of ions, strong acid or base. Okay. Concentration is how packed together you are. Molarity, how many moles in your liters. How many moles in your liters? If there's a lot of moles in your liters, it's concentrated. If there's not a lot of moles in your liters, it's dilute. So we're going to say molarity, 1 molar or higher is going to be concentrated, and less than 1 molar is going to be dilute. All right. So, oh look, we have to decide if this is an acid, a base, and if it's strong or concentrated. So hello, I'm an acid. So let's talk about strength first. We don't even need that number. We look back on the list and yay, it's HCl. This is an acid. It is strong, which means it dissociates completely, and this means it's dilute because that molarity is less than 1. Hello, I'm an acid. I'm on the list. I must be strong. It's an acid, and it's strong, which means it dissociates completely, and then it's 10 molar. 10 molar is greater than 1, so it is concentrated. Concentrated. Okay. Hello, I'm an acid. So we check. Not on the list. This is an acid. This is weak. And it's 0.2 molar, which is less than 1, so it's a dilute weak acid. Right. Hello, I'm an acid. Start with hydrogen. Alright, so that takes care of the acid part. That's that. Let's look. HF is not on the list. Get rid of some of that, Harbin. Okay, so HF is not on the list, which means it's weak, because that was the strong list. And then it's over 1, so it's concentrated. Wow, who writes this sloppy? I do. Okay, NaOH. Hey, that's a base. That's a base. Alright, so we know it's a base. Then we look, group 1, group 2. Oh, look, there's sodium. NaOH is a group 1 metal. So it's in a base, and it's strong because it's in a group 1 or 2. It's with hydroxide. 2 molar is concentrated. Hello, I'm an acid. Oh, you're a base. Okay, indicators. We talked about indicators. We talked about litmus. Litmus is either blue or red, depending on what it's put into. Okay, but what's cool about it is it's like equilibrium. So this means acid, litmus, because it's got the H in front, and the litmus molecule is complicated, so we'll just write LIT for short. All right, so it's an equilibrium. If we use Le Chatelier's principle to work out what would happen if we added hydroxide ions. Okay, hydroxide ions are OH minuses. OH minuses combine with H pluses. So if I put this in, it'll pull that up. What happens when you leave a hole? Shifts to fill the hole, so it's going to turn blue. Hydroxide is a base, so litmus turns blue in base. Litmus, blue in base. Blue in base, because the base removes the hydrogen, shifts the equilibrium over to the blue side. What if we added more hydrogen ions? So now, instead of taking them away, we add acid. Acid adds more of this. That shifts to the right. I said right, but I mean left. Okay, so shifts left. So litmus is going to be red in acid. And it's all about the equilibrium. Isn't that cool? More acid makes the color of litmus shift to the red side. Woohoo! Okay, hey, phenolphthalein, another indicator. This is phenolphthalein in acid form. This is phenolphthalein in base form. If we add acid, we're adding H+. Okay, more H+. So more H+, stresses out this side, it'll shift this way, it'll turn clear. Turn clear. Yeah, phenolphthalein turns clear in acid. Base is added is adding more OH-. More OH-. So more OH- takes this and reacts, pulls it out. So it turns pink in base. All right? Yay! You gotta love indicators. Because look how colorful they are. There are so many different indicators. In fact, things in your kitchen like cabbage. Red cabbage is an indicator. And it turns different colors in different acidity and with different acids and bases. So all of these things, and here's our phenolphthalein, woohoo, okay. And litmus is here. So those 2 indicators on here plus others. So colors tell you if you have acids or bases. Okay, it's just a review. Hello, I'm an acid. Hey, let's get some music going. Hello, I'm an acid. That means I'm friendly. Hello. And I have an H+, and I give it away. Okay. Every acid has a conjugate base. Every base has a conjugate acid. Concentration does not equal strength. Okay, this is molarity, and this is ionizing. Right. Indicators change color at different pHs. Make sure you know the props and your strong acids and strong bases. Oh, look, it's time to go. Read your books. Know these things. Peace out.